In the quiet vacuum of space, 3I/Atlas will glide past Mars. Just another comet, or so it seems. But Harvard scientists are alarmed. Despite raging jets of gas, its trajectory barely shivers. Evidence that 3I/Atlas is staggeringly massive, weighing in at over 33 billion tons with a nucleus the size of a mountain. That's orders of magnitude beyond anything seen from previous interstellar visitors. If 3I/Atlas really is getting bigger, why is it so immune to the forces that shove ordinary comets off course? And if the mainstream explanation doesn't fit, what on Earth, or beyond it, could we actually be seeing? Pinpointing the true path of an object like 3I/Atlas begins with a discipline that's as much art as science: astrometry. Every night, telescope operators around the globe lock onto a faint speck against the shifting grid of background stars. The goal is simple to state: measure the comet's exact position in the sky down to a fraction of an arcsecond. But the execution is anything but. Modern digital detectors known as CCDs capture the faint glow of Atlas's coma and pinpoint its center of light, or centroid, with astonishing precision. For the best-equipped observatories, a single exposure can yield positional accuracy on the order of a few milliarcseconds, less than the width of a human hair seen from a mile away. But no measurement stands alone. Each image is cross-referenced against a catalog of reference stars, themselves mapped by missions like Gaia to an accuracy that would have seemed impossible a decade ago. The process is meticulous. Telescope clocks are synchronized to coordinated universal time, and every exposure is tagged with the precise moment it was taken. Even small errors, like using local time instead of UTC or referencing an outdated star catalog, can nudge the apparent position by a measurable amount. To guard against this, teams apply statistical corrections, recalibrating each night's data against the latest star charts and flagging any observatory that consistently reports outlier positions. The result is a time-stamped trail of Atlas's journey, each data point a product of careful alignment, calibration, and error checking. When astronomers talk about trajectory residuals, the tiny differences between where Atlas is expected to be and where it actually appears, they're relying on this foundation. The confidence in later claims about mass, acceleration, or rarity rests on the bedrock of these nightly measurements. Without this level of precision, the story of 3I/Atlas would be lost in the noise of the stars. Before any claims about Atlas's size or mass could be trusted, the Harvard pipeline architects took on a task as daunting as the observations themselves: purging the data of hidden biases. The numbers, once they were finally clean, told a story that few expected. By cross-calibrating photometric data from dozens of telescopes, analysts pinned down Atlas's apparent brightness across multiple nights and filters. The process hinged on a handful of assumptions: the reflectivity, or albedo, of the nucleus bracketed between 0.04 and 0.06, in line with some of the darkest comets ever measured, and a plausible range of densities from porous ice to denser, rockier mixes. Plug those values into the standard equations, and the math points to a nucleus pushing 5 kilometers across. That's not just big for an interstellar visitor, it's big, period. Most comets that cross the inner solar system are a fraction that size. Even Bernardinelli-Bernstein, the so-called monster comet, only slightly outpaces it. But here's the kicker: the force calculations derived from trajectory residuals and the observed coma don't budge that estimate. The measured non-gravitational acceleration, less than 15 meters per day squared, is so small that for the observed level of outgassing, only a body of immense mass could resist being nudged off course. The numbers converge: a nucleus at least several kilometers wide with a total mass exceeding 30 billion tons. It's a result that held up under every permutation the analysts threw at it. Monte Carlo runs, density tweaks, even alternative force models. Each time the lower bound stayed stubbornly high. For the first time, the interstellar comet catalog had a heavyweight contender, and the implications rippled through every corner of the research community. Shock hit the Harvard Working Group before dawn. The final mass figures had barely circulated before Slack channels flared with disbelief. In the world of interstellar objects, size is everything. And Atlas's numbers didn't just break the curve, they shattered it. For context, every interstellar object cataloged so far, Oumuamua Borisov, was a cosmic pebble by comparison, small enough to be flicked off course by a puff of gas. Atlas, at over 30 billion tons, stood alone. The prevailing models built on years of survey statistics predicted that such a massive active interstellar object should be vanishingly rare. So rare, in fact, that some theorists argued we might never see one in a human lifetime. Within hours, the crisis spilled beyond Harvard. Emergency teleconferences drew in teams from NASA, the European Space Agency, and the Minor Planet Center. The numbers were double-checked, then triple-checked. Yet the mass held firm no matter which pipeline ran the data. Some researchers scoured the literature for plausible outliers. Others dove into population models, trying to square this detection with the expected frequency. The answer was always the same. The odds of finding a kilometer-scale outgassing interstellar object in the current survey era were, at best, orders of magnitude lower than the chance of a smaller visitor like Oumuamua. Most models suggested a drop-off so steep that Atlas's appearance felt almost like a statistical fluke. The tension was obvious in every exchange. Some called for caution, raising the specter of hidden biases or unmodeled physics. Others, more blunt, called it the most improbable find in decades. By the end of that week, the consensus was less about what Atlas was and more about what it wasn't: ordinary. The field had been handed a puzzle that defied the numbers, and the search for answers was only beginning. The debate around 3I/Atlas's true nature now plays out across a spectrum, from what's firmly established through plausible but unproven to the outright speculative. At the foundation sits the consensus view. NASA, ESA, and most planetary scientists describe Atlas as a massive natural interstellar comet. Its coma, nuclear size, and trajectory all fit within the broad, if stretched, boundaries of comet science. Agency statements stress caution, pointing to the robust mass estimates but urging patience for more spectroscopic and imaging data before rewriting the textbooks. Almost certainly a comet, as one JPL scientist put it. But the mass estimate, "I'll sleep better once we see the Mars pass spectra." Above that baseline, a layer of plausible but unusual features fuels deeper curiosity. Atlas's orbit, for one, is nearly coplanar with the ecliptic, the plane shared by the major planets. That's a statistical oddity for an interstellar visitor, whose paths are usually scattered at steep angles. Its path brings it close to Mars, then onward toward Jupiter as if threading a cosmic needle. Some researchers argue this could be a quirk of random sampling, or perhaps a hint at rare dynamical histories in other star systems. Still, these ideas remain within the realm of natural but improbable. At the speculative end, Avi Loeb and a handful of collaborators have floated the idea that Atlas might be more than a comet. The argument hinges on the mass-to-acceleration mismatch and the alignment of its orbit. Loeb is careful to frame these as open questions, not conclusions. If 3I/Atlas is truly a billion-ton object defying our models, we must be open to possibilities outside the norm, while sticking to the data. The techno-artifact scenario, an engineered probe or derelict, sits here, intriguing but unsupported by direct evidence. NASA and ESA push back, warning against letting speculation race ahead of what's observed. Confidence tier graphics now accompany many presentations: established, plausible, speculative. Each claim is slotted by its evidentiary weight. As the observing campaign ramps up, the field holds to a simple rule: extraordinary claims require extraordinary proof. David Falzner's planet seeding hypothesis pulls the debate out of the solar system and into the heart of galactic evolution. In his simulations, young star systems don't just sweep up local dust. They act as cosmic nets, capturing stray interstellar objects that wander too close. The logic is simple. More massive stars build larger, denser disks, and their gravity reaches farther. Theoretically, this gives them more chances to snare passing bodies like 3I/Atlas. But when Falzner's models are scrutinized, the optimism fades. The capture rates climb with stellar mass, but the numbers are still small. Even in the most favorable scenarios, only a handful of interstellar objects are expected to be trapped during a disk's short window of opportunity. Peer reviewers poring over the simulation outputs question whether the known population of objects this size is anywhere near enough to make a difference. One reviewer's comment leaked from the 2025 submission: "The premise is elegant, but the statistics are not on its side." The broader astrophysical stakes are clear. If planet seeding by interstellar objects is real, then every detection, especially one as massive as Atlas, could represent a missing link in how gas giants form around high-mass stars. But the evidence remains circumstantial. There's no direct record of a captured object sparking planet formation, and the frequency of such events is buried beneath layers of uncertainty. Falzner's own graphs show a qualitative trend: bigger stars should, in theory, capture more interstellar debris. Yet the models stop short of quantifying exactly how much more, or whether the effect is strong enough to matter on a galactic scale. For now, the planet seed idea sits in a liminal space: imaginative, mathematically plausible, but lacking the hard numbers that would turn a trend into a law. As observation campaigns ramp up, the field watches for signatures that could tip the balance. Isotopes, dust chemistry, or orbital clues that might reveal a true interstellar origin. Until then, the debate continues, rooted in possibility, held in check by skepticism. The countdown begins in earnest as 3I/Atlas sweeps toward its next rendezvous. Mission planners across 3 continents have circled 4 dates, each a window of opportunity and risk. First, early October. Mars Express and ExoMars TGO, both in orbit around Mars, are slated to train their cameras and spectrometers on the interstellar visitor as it passes within millions of miles of the red planet. The timing is tight, with final targeting instructions often arriving hours before closest approach. Atmospheric spectrometers originally designed for Martian weather will now hunt for faint traces of water, carbon dioxide, and metals in Atlas's coma, hoping to catch the first chemical signatures from outside the solar system. Late October brings perihelion, the moment Atlas swings closest to the Sun. At this point, ground-based telescopes lose sight as the comet vanishes into solar glare. Only spacecraft with the right vantage, some in solar orbit, some trailing behind Earth, can monitor its activity. Teams at the Minor Planet Center and ESA's Solar Orbiter coordinate alerts, watching for sudden changes in brightness or trajectory that might betray new jets or structural shifts. By December, Atlas emerges from behind the Sun and makes its post-perihelion approach toward Earth, passing at a distance of roughly 170 million miles. This is the window for the James Webb Space Telescope and Rubin Observatory. Both will attempt high-resolution spectra, searching for isotopic fingerprints and dust composition that could clarify the object's origins. Finally, March 2026, Atlas is projected to skim above Jupiter's cloud tops, possibly within 33 million miles. NASA's Juno spacecraft, already in a polar orbit, may be retargeted to sample dust streams if mission controllers approve. Each milestone is a test of instruments, of planning, and of the theories that have built up around this extraordinary traveler. Every research team now keeps a live checklist, an evolving watch list of measurements that could break the tie between natural and exotic origins. At the top, isotope ratios in the coma gases. If Atlas's hydrogen or carbon isotopes stray far from solar norms, it could signal a birthplace beyond the familiar spiral arms, or even processes not seen in standard comet chemistry. Next, the dust-to-acceleration metric. Here's the logic. If the coma's dust output remains high while the trajectory stays stubbornly unperturbed, the mass estimate only grows more unyielding. A mismatch, lots of dust but no measurable push, would be a red flag for hidden mass or non-standard forces. Torque analysis is another diagnostic on every whiteboard. Most active comets reveal themselves in their spin. Outgassing jets act like thrusters, subtly twisting the nucleus and leading to a telltale wobble in the light curve. If Atlas shows a perfectly steady rotation, or a torque pattern that can't be matched to observed jets, then theorists will press for alternative explanations. High-cadence photometry from Rubin and JWST will look for these minute shifts, sometimes only a fraction of a degree per day. Spectral chemistry rounds out the list. Unusual metals, especially nickel-to-iron ratios, will be scrutinized for signs of fractionation or artificial enrichment. Raw spectra from Keck and JWST archives will be pored over line by line to rule out calibration errors before any extraordinary claims are made. Each new data point, an isotope anomaly, a dust acceleration gap, a torque irregularity, lands like a fresh clue. With every orbit, the evidence grows and the field waits for the pattern that will finally tip the scales. Harvard's analysis confirmed that 3I/Atlas has a nucleus nearly 5 kilometers wide and a mass exceeding 33 billion tons, making it at least 1,000 times heavier than any previous interstellar visitor. Despite visible outgassing, its non-gravitational acceleration remains below 15 meters per day squared, a mismatch that defies standard comet models. While most agencies maintain a natural origin, the object's size and near-ecliptic approach have sparked debate, including proposals for both technological artifacts and planet seed roles. Scheduled flybys, Mars Express and ExoMars TGO in October 2025, JWST and Rubin after solar conjunction, and a possible Juno encounter at Jupiter, will deliver the decisive data, isotope ratios, dust output, and spin changes. To date, fewer than 1 in a million known interstellar objects match 3I/Atlas's mass. The coming months will test every theory on the table. For now, the evidence leaves one fact clear: 3I/Atlas is unlike anything seen before, and its true nature remains an open question.